Welcome to The Explainer. Today, we're jumping right into a hidden, incredibly high-stakes conflict that's happening right inside our power plants. We're talking about a literal battleground where massive, heavy-duty piping meets hypersensitive, high-speed machinery. It is this wildly delicate balancing act of forces, temperatures, and pressures where, honestly, just one tiny miscalculation can bring an entire power plant to a grinding, catastrophic halt. Okay, let's dive right into this. Have you ever wondered what actually happens when plant piping pushes back on a multi-million-dollar turbine? You see, industrial piping isn't just static metal sitting there. As fluids heat up and pressurize, those pipes expand, they shift, and they exert tremendous forces, which we call nozzle loads, right onto the sensitive machinery they connect to. The stakes here are absolutely massive. We are talking about preventing catastrophic failures right at the heart of our energy grids. And that brings us to this fundamental, pretty stark warning from our source material. Use of some common general plant piping practices could lead to real problems in power plant machinery. Basically, the rules that work for your standard everyday plumbing or even just general plant setups, they can literally be disastrous when you apply them to the dedicated, highly sensitive rotating equipment in a power generation facility. The margins for error are just on a completely different planet. So this creates a really fascinating natural conflict. In one corner, you've got the piping designers. They obviously want higher allowable nozzle loads to simplify their incredibly complex layouts. It makes their piping designs and their support structures way easier to build. But in the other corner, you have the machinery manufacturers, and they want the absolute smallest loads possible to protect their equipment. They need perfectly tight alignment, rock-solid reliability, and zero operational complaints. So who wins this engineering tug-of-war? Well, from the power plant operator's perspective, where long-term reliability is the only thing that actually matters, the machinery manufacturer has to win. The machines simply must be protected at all costs. So here is our roadmap for today. We'll explore the engineering tug-of-war, navigate the industry standards, look at the very real dangers of misalignment, break down support design rules, uncover a huge trap with thermal expansion, and finally, look at the sheer power of asymmetry. Section 1. The engineering tug-of-war, piping versus machinery. Let's really dig into what's at stake when these two distinct systems collide. Think of a power plant like a giant living organism. The rotating machinery, like a massive steam turbine, for example, is the beating heart of the operation. And the piping network? That acts as the veins and arteries, delivering high-pressure steam and fluids. But if those heavy steel veins push and pull too hard on the delicate valves and nozzles of the heart, the entire system fails. The alignment gets completely thrown off, and the heart literally tears itself apart from the inside. The whole goal of power plant engineering is to design a piping layout with enough flexibility so that the heart is never crushed under the sheer weight or thermal expansion of its own veins. Section 2. Navigating industry standards, the rules of engagement. Because this relationship is so vital, the industry definitely doesn't just guess at what's safe. Now, what's really interesting about this is how carefully different equipment is categorized and protected by highly specific codes. Take steam turbines, for instance. They're governed by NEMA SM23. That's the baseline. Though admittedly, sometimes buyers try to push for 1.5 times that limit just to make their piping designs a little easier, which frankly requires super careful verification. Then you've got API 610 for critical pumps, like boiler feed water pumps. If those nozzles are larger than 16 inches, you usually have to sit right down and hash out the limits directly with the vendor. Centrifugal compressors use API 617, permitting loads around 1.85 times the NEMA standard, while screw compressors rely on API 619. And for specialized machines with incredibly tight internal clearances, like axial compressors, engineers often have to enforce even lower load limits than these standard codes suggest. But what actually happens when the piping designers push a little too hard? Section 3. The dangers of misalignment. When the heart fails. Excessive pipe loads on a rotating machine cause absolute havoc, and it starts with the physical distortion of the equipment casing itself. This leads directly to the internal misalignment of the machine's rotating shafts. Steam turbines are especially vulnerable here. When those internal components misalign, they start rubbing together. You get accelerated wear. The couplings connecting the machinery begin to strain, which causes high vibration levels that can and will trigger automated safety trips and entirely unscheduled power outages. If left unchecked, this misalignment eventually leads to catastrophic coupling or bearing failure. The machine essentially destroys itself from the inside out. Section 4. Support design best practices. Busting plant myths. To prevent these million-dollar disasters, engineers rely on some very specific rules for the piping supports. First up on our myth-busting list is a practice known as dead weight balance at operating condition. In normal, general plants, engineers sometimes set their spring supports so they only balance the heavy weight of the piping when the system reaches its extremely hot operating temperature. The argument is that this minimizes stress during operation to prevent the metal from creeping. But in a power plant, this is incredibly dangerous. To make this work at all, the spring supports have to be physically locked in place during installation. When the system is finally ready and those locks are suddenly removed, the piping can undergo this severe twisting, jerking motion. It's totally unpredictable, incredibly risky, and frequently imposes massive, sudden loads right onto the turbine nozzles, causing instant alignment problems. Let's contrast that rather dangerous method with what the technical note highly recommends: dead weight balance at ambient condition. This simply means the piping system's dead weight is entirely absorbed by suitable supports while the plant is at room temperature. The piping fit-up is done with the spring supports completely unlocked from the very start. You adjust the supports right then and there to bring the load on the machine's nozzles down to near zero. While, sure, some load will occur when the system heats up, that operating load is highly predictable. This approach eliminates those violent jerks entirely, makes field adjustments a breeze, and is just infinitely safer for the delicate machinery. To make absolutely sure everything stays safe, there are 3 very strict steps for installation. Step 1, you must perfectly align the rotating machinery all by itself, with 0 piping attached. Step 2, you carefully adjust and weld the piping spools for a proper fit. And finally, step 3, you closely observe the alignment of the machinery as the piping is actually being bolted on. If you see excessive movement in the machine during step 3, you stop. The piping system absolutely must be modified or readjusted until that misalignment is brought back within the permitted limits. No exceptions. Section 5. Managing thermal expansion joints. The anchor trap. Remember, piping gets incredibly hot, which means the metal expands, and that brings us to a massive engineering trap. When pipes heat up, they grow. To accommodate this, engineers usually add loops or bends to the piping to give it some natural flexibility. But sometimes, especially for very large pipes with very low equipment load limits, they get tempted to just use an expansion joint. Think of it like a flexible metal accordion right at the equipment nozzle. But the consensus here is crystal clear. Expansion joints should only be used as the absolute last resort. A much better modern approach is concurrent modeling, where you design the machine and the piping together on a computer to optimize the whole system's natural flexibility. But if you absolutely must use an expansion joint, there is a massive trap you have to avoid. So the crucial point is this. In general plant piping, engineers often use heavy bankers on expansion joints to resist pressure forces. But you should never, ever use these anchors near a rotating machine. Notice the terrifying chain reaction this causes. When the plant starts up, the piping system heats up. Both ends of the expansion joint naturally expand inward. When that happens, the tie rods holding the system suddenly go completely slack. Instantly, the pressure pushing against the machine becomes unbalanced. Instead of the smooth, natural flexibility you were hoping for, this sudden shift results in an unpredictable, violent transient load hitting the machine, which is often more than enough force to shove the turbine right off its alignment. Section 6. The power of asymmetry. Breaking the rules. We've just seen how standard rules can cause major problems. So let's look at a technical concept that flips a fundamental engineering principle completely on its head. In almost all fields of design, symmetry and balance are celebrated as the absolute gold standard. A very common solution for piping expansion is a 3-hinge system. But interestingly, a perfectly symmetric 3-hinge straight-line piping system can actually get physically stuck. If you have a hinge at each end and one perfectly dead center in a straight line, it mathematically refuses to move when the temperature changes. Because of that perfect symmetry, the middle hinge just gets completely stuck, and the expanding metal instead pushes outward with unexpectedly massive, unmanageable forces that conventional supports simply cannot handle. And this brilliantly illustrates why you sometimes have to break the rules. By designing an unsymmetrical layout, like an L-shaped piping route, you completely solve the problem. By building in just a little bit of imbalance, you force that middle hinge to be active and to actually absorb the thermal expansion. According to the source material, in one specific case study, simply shifting to an unsymmetrical design reduced the unwanted movement to less than 7% of what it was in the symmetric design. Less than 7%. That makes it totally manageable for the supports. Which brings us to our final thought for this explainer. Consider just how wonderfully counterintuitive the world of heavy industrial machinery really is.
General rules become hazards, safety anchors become traps, and perfect symmetry becomes a physical roadblock. In engineering, symmetry is usually the ultimate goal. But when we are trying to protect the beating heart of a power plant from the massive shifting forces of its own piping, we have to recognize the reality in front of us. Could a little imbalance actually be the key to perfect harmony? It really makes you look at the incredibly complex systems that power our world in a completely different light.